Hello, I'd like to introduce you to this visual guide to reservoir engineering and introduce myself, Dr. Andrew Wadsley. I've been a reservoir engineer for over 45 years, having started as a well site petroleum engineer with Shell International in Brunei in 1975. In this video series, we'll start with the basics, then look at classical analysis methods, including decline curve and fractional flow analysis, and finish with advanced topics such as dynamic reservoir simulation and petroleum reserves estimation. I've used all of these techniques in my consulting while teaching at university and acting as an umpire in gas and oil disputes. However, my most rewarding time was working with Dake, both in my RE 101 class with Shell and later as a consultant in London. Before we move on, if you hear Tinkerbell, then the slide is about to transition. Click pause if you want to stay on the slide a little longer. So, what are we doing with this course? Well, the objective is to introduce, as far as I see it, the important topics of reservoir engineering, from basics such as petroleum reservoir traps, porosity, permeability, etc., intermediate topics such as multi-phase flow, decline curve and fractional flow analysis, and to finish with an introduction to reservoir simulation and gas and oil reserves estimation. In all, the course is comprised of 20 parts. The presentation is a little different to the usual. We call it a visual guide because the course content is illuminated by lots of diagrams, figures and images. The scripts associated with each slide are also spoken. Research has shown that maximum understanding is achieved for simultaneous seeing and hearing. I hope you enjoy it and look forward to talking with you in interactive sessions and workshops. To introduce our subject, let's meet a reservoir engineer, or at least my idea of one. A reservoir engineer studies oil and gas reservoirs. The basic job is to predict the amount of oil and gas that can be recovered from these reservoirs and the best way this can be accomplished. Most of the time, the job is difficult because there's no way you can actually see the reservoir. That ladder isn't going to help either because most reservoirs are thousands of meters under the ground. It's a long way down. What's the role of the reservoir engineer within the corporation? Your job is to collate and interpret data collected during the exploration and appraisal phases of reservoir development. Using this data, you calculate initial hydrocarbons in place and define the recovery or drive mechanism in the reservoir, and then optimize placement and location of production and injection wells as required. Using appropriate reservoir models, you generate production profiles for input into the field development and reservoir management plans. You then use these production profiles and plans to calculate oil and gas reserves and quantify risk and uncertainty with respect to reservoir development. Let's summarize what is a reservoir engineer. A reservoir engineer is a person who is able to describe and quantify the behavior of reservoir fluids and hydrocarbon-bearing formations when these are produced. That is, you are a physicist. But the reservoir engineer also plans the development of the field, including wells, production facilities, and the hydrocarbon gathering and water or gas injection systems. That is, you are an engineer. The reservoir engineer also quantifies the recoverable hydrocarbons, the production through time of gas and oil, the economics of the field development, and thereby calculates hydrocarbon reserves, expected net present value, and the financial risk associated with the field development. That is, you are an economist. Further, you ensure that the development meets both corporate and community expectations for responsible exploitation of the resource. That is, you have a broad social responsibility. Before we start, let's look at a quote by Dr. A.S. O'Day from his article, Reservoir Simulation. What is it?
In general, simulation refers to the representation of some process by either a theoretical or a physical model. Here, we limit ourselves to the simulation of petroleum reservoirs. Our concern is the development and use of models that describe the reservoir performance under various operating conditions. We in the petroleum industry are in the reservoir simulation revolution. As time goes on, simulators will be used more and more, so a basic understanding of reservoir modeling is essential. The engineer, especially, must become competent in setting up simulation problems, in deciding on appropriate input data, and in evaluating results.
O'Day wrote this article in 1969, when the analysis of oil and gas reservoirs was carried out primarily using classical engineering methods. Since this time, reservoir simulation models have grown in complexity, but are still subject to a fundamental requirement that the models so constructed be useful predictors of future reservoir performance. The word useful is important here. Reservoir models need to be fit for purpose. The level of detail required in a model should suit the required purpose of the model. The art of reservoir engineering is to start with the simplest possible model appropriate to the business decision, and only add detail as required. In the following, we shall look at a range of reservoir models, both simple, or classical, and complex, including dynamic reservoir simulation. Looking ahead, what do we mean by fit for purpose? For example, if the purpose of the model is to predict the pressure history of the reservoir under various production and injection scenarios in the case of gas storage, then a simple gas reservoir model, such as a tank, may be all that is required. On the other hand, if the model is to be used to predict infowell performance in a three-phase gas-oil-water reservoir, a detailed geocellular model near the infowell locations may be necessary to provide a reliable forecast. Such reservoir models will be discussed in more detail later. For us to know what challenges a reservoir engineer faces and how to choose the best reservoir model and solutions, we must understand and consider several properties of the total reservoir system. So we're going to be concerned with 5 things: the properties of the reservoir rock, the properties of the fluids in the reservoir, the types of oil and gas reservoir, the laws of physics governing the way fluids flow in rocks, and, finally, the energies which push fluids out of the reservoir, called reservoir drive mechanisms. Hi, we're now going to look at some of the main types of geological structure that form gas and oil reservoirs. Petroleum reservoirs are normally found in sedimentary rocks. Rarely, petroleum is found in fractured igneous or metamorphic rocks. Igneous and metamorphic rocks originate in high pressure and temperature conditions that do not favour the formation of petroleum reservoirs. Sedimentary rocks are the result of geological processes, weathering, erosion, deposition, that occurred over very long periods of time. Different geological depositional settings have led to sandstone, carbonate, or conglomerate rock formations which have been deposited in sequences overlying each other over tens of millions of years. Geological structures result from the powerful tectonic forces that occur within the Earth's crust. These forces fold and break rocks, form deep faults, and build mountains. Repeated applications of force, the folding of already folded rocks, or the faulting and offsetting of already faulted rocks can create very complex structures. Let us define what a reservoir is. A reservoir is a container. The container is buried beneath the surface of the earth and is made up of rocks. The buried rock reservoir has no walls, top or bottom in the conventional sense. If there are any fluids in the reservoir, the fluids are kept in by barrier rocks. The barrier, or seal, is usually made up of rocks of a type different from the rocks that make up the reservoir. Once migration stops, the fluids in the reservoir are usually gas, the gas cap, overlying oil, the oil column, which overlies formation brine, the water leg. Let's talk some more about seals and barriers. Seals can be created by a salt plug or dome, as shown here. Note the barriers that have been formed by the impermeable salt. The salt forms a seal so that gas and oil cannot rise any further in the reservoir rock, which has been truncated against the salt. The salt dome traps the hydrocarbons in the reservoir. Barriers to hydrocarbon migration can also be created by layers of impervious rock, such as shale, which lie above the reservoir rock, which is typically sandstone or limestone. You can see here that all the layers of the rock, or strata, are folded, trapping the hydrocarbons beneath the seal. This sort of barrier is called an anticlinal trap. Sometimes a fault may move impervious layers of rock opposite a reservoir. This is called juxtaposition. When this happens, the impervious layer makes a barrier with hydrocarbons in the reservoir trapped against it. Faults themselves may be sealing or non-sealing, depending upon the amount and permeability of any clay or shale gouge along the fault. If they are non-sealing, then hydrocarbons may migrate up the fault or into a permeable strata juxtaposed against the primary reservoir rock. A common hydrocarbon trap is formed by structural rollover into a fault. The intersection of the top reservoir and the fault is often a leak point, with gas and oil leaking up the fault, which controls the depth of fill of the trap. Also shown in the figure is a synclinal spill point and a reservoir-reservoir juxtaposition across the fault, which can also allow hydrocarbons to escape the trap. Faulting in reservoirs can be very complex, leading to multiple disconnected accumulations of gas and oil. Here, an overthrust structure is shown, where the rock strata are folded over, being pushed by compressive forces along a reverse thrust fault. In this case, there are two hydrocarbon accumulations, one vertically above the other, leading to multiple gas-oil and oil-water contacts. Remember, for gas and oil to be present in a reservoir, they must be trapped in some way. Here, the oil is trapped in a layer of sandstone that is surrounded by impervious rock. However, sometimes a trap may be present, but it may contain only brine or salt water and no hydrocarbons. In such cases, the only way we can tell if gas or oil is present is to drill a well. Until the well is drilled, there is no certainty whether hydrocarbons are trapped. The final trap we consider is the carbonate reef trap, which is similar to a stratigraphic trap. Carbonate reefs form in a limited range of temperatures, water depths, salinities, and wave activities, but form some of the most prolific gas and oil reservoirs. The basic terms used to describe gas and oil accumulations are shown in the figure. The gas-oil contact is the depth of the interface between the gas and oil, GOC. The gas-water contact is the depth of the interface between gas and water, GWC. The oil-water contact is the depth of the interface between oil and water, OWC. The spill point is the maximum depth at which hydrocarbons can be trapped. The reservoir closure is the vertical distance between the top of the reservoir and the spill point. Gas, oil and water up to and down to are the depths of the shallowest and deepest intersections of the fluids in the borehole. Analysis of reservoir structure must also take into account aquifer systems. All reservoirs have a water leg, and this may be connected to an aerially extensive aquifer system, which may cover an area of thousands of square kilometers. The image shows, schematically, three systems: no aquifer, limited aquifer, and aerially extensive aquifer. As discussed later, each of these systems contributes differently to the pressure response of the reservoir during production. The lower image shows the large extent of the Gippsland Basin aquifer, which outcrops onshore and is recharged with meteoric water, with a significant salinity gradient increasing offshore. The aquifer has an aerial extent exceeding 22,000 square kilometers. Okay, the previous slides were a very quick introduction to the main types of reservoir traps. Of course, real reservoirs are often much more complicated than the example shown here. Generally, the secret to good reservoir engineering comes from having a good geologist working alongside you and building a coherent, consistent structural and depositional model. Anyway, let's move on and investigate the storage of fluids and subsurface rocks, that is, reservoir porosity, discussed in the following Part 2.